Yasu Furukawa, a PhD student at University of Urbana-Champaign with Champons. Yeah. Now he's in France, right?
Yeah, he left UIUC forever.
I met Yasu almost 2 years ago now.
Yeah.
Oh, once a month and a half ago. At the University of Magic, he was doing an internship there, and we collaborated on a stereo reconstruction program. And he's done a lot more work in this area, so he's going to tell us some stuff about it.
Yeah, thanks, Franco. Thanks, everybody, for coming. I'm Yasutaka Furukawa, and I'll be talking about image-based modeling, or multi-view stereo, and it's a joint work with Jampans, who is my advisor. So what is image-based modeling? Well, it's about reconstruct 3D geometric information from images. Then there are whole different kinds of computer vision algorithms that use images to do 3D reconstruction. But our problem is our often called multiple view stereo or multi-view stereo, which is kind of just one category of image-based modeling methods. And images can contain various objects, like, let's see, use my pointer, objects of some, like a toy, like depicting our Roman soldier, or could be some sculpture. It could be some face or some real human skull. It's for the anthropologists who are interested in analyzing the shapes of skulls. And it could also could be images of some outdoor scenes with some water. And it could also images of some buildings where you see pedestrians in front of it. So in this example, you want to do 3D reconstruction on this building while ignoring pedestrians. Also, by the way, feel free to stop me and ask questions at any time. So more formally, we focus on a problem that takes a set of images with camera parameters. So we assume that the camera parameters are already given, so cameras are calibrated. And we are going to reconstruct 3D geometric information of objects or scenes that are rigid with respect to the cameras. So that's kind of a key kind of idea. So in the previous slide, you see the people in front of the building. And if you take a picture of the building like from multiple viewpoints, those people probably have moved. So those people are not rigid in the 3D scene. So those are, whatever object which is not rigid is considered as outlier, an obstacle. So we ignore them. So our purpose is to reconstruct a rigid structure in the 3D scene. And you see just one example. You take a picture of my face for 4 different viewpoints. And this is our picture taken at the same time. So my face is rigid. And we are going to do some 3D reconstruction. And you can get a model like this. And I'd like to mention why this problem is important. First of all, in comparison to laser range scanner, which is kind of popular for computer graphics applications, we would like to address a couple of advantages over laser range scanner-based methods, which is, first of all, we use just cameras for data acquisition, which is cheaper than laser range scanner. And if you count the number of pixels in the cameras, or if you look at the lateral resolutions of the devices, cameras have much more pixels than laser range scanner. Laser range scanner gives you some depth map, but the number of pixels are much fewer. And also, the cameras are fast or higher frame rates. That's kind of 2 key advantages over the laser range scanner. But of course, the disadvantage is the depth accuracy or vertical resolution. According to some quantitative evaluations of this multi-view stereo algorithm, you see right here that if you use our kind of latest, one of the state-of-the-art image-based modeling methods, the accuracy of reconstruction is about 0.5 millimeter for an object of about 15 centimeter in diameter, so about this objects, and about 0.5 millimeter in accuracy if you use our kind of set of low-resolution images, 640 by 480 images. While if you pick one laser range scanner brand here, which costs about $15,000, then according to their spec, the accuracy of depth measurement is 0.1 millimeter for an object about 15 centimeter. But the couple of things to note is for this result, for this image-based modeling result, we use really low-resolution images, 640 by 480. You can just use higher resolution camera, maybe 16 megapixel or 12 megapixel. Then this result should just become much better. And also for this laser range scanner, typically you want to get a single nice model. You have to scan from multiple viewpoints by using laser range scanner. Then merge them into a single 3D model. So typically, there's some manual work to register those depth map. And additional errors can introduce in that post-processing. So I guess the image-based modeling method is kind of equivalent or a good competitor for laser range scanner-based methods. And I also like to mention another advantages, more like advertisement, but here are some situations where we can capture 3D geometry by using cameras, but not by laser range scanner. For example, if you go to NASA website, you can download some images of an asteroid, like rotating in the space. And ultimately, we can just use our kind of standard camera calibration program, like structure from motion, and get camera parameters and run our system to get 3D reconstruction. But if you want to capture 3D geometry with the asteroid in the space by using laser range scanner, you have to ship your scanner to the space, which is expensive, and you don't want to do. And another situation is if you want to capture like fast motions, like facial motions, or more non-rigid object, because our cameras are fast, we can kind of do, for example, frame-by-frame reconstruction. But laser range scanner is too slow and cannot capture like facial motions. And the last extreme example is some people are interested in reconstructing objects like 100 years ago, which is showing this picture. This is the kind of famous kind of cultural heritage, our steps, which has been there for like 100 years. And actually, there are some people interested in reconstructing structure 100 years ago, because this structure has been eroded for years, like wind or rains. And for those people, they're actually images taken 100 years ago. It's black and white images. But actually, we can use those images to 3D reconstruction. Actually, one of my colleagues has done that. But you cannot use laser range scanner to capture this structure 100 years ago, because you don't have laser range scanner back that time, and you don't have a time machine to ship laser scanner back 100 years ago. So there are situations where you want to use cameras instead of the laser range scanner. So here's the overview for the rest of my talk. First, I'm going to talk about a function called photometric consistency function, which is kind of really general fundamental idea in multi-view stereo. This is kind of introduction for people who doesn't really know about reconstruction. Then I'm going to talk about the main ideas of our algorithm. Then talk about the algorithm in detail, show some results, and refer to some future work. So any questions so far? Okay, so far so good. So first, I'm going to talk about the photometric consistency function, which is really key an idea in 3D reconstruction. So the real basic of how to estimate 3D depth from multiple cameras is really simple. It's just what you do with your two eyes. If you close one eye, you can really estimate depth information. While you have two eyes, you can kind of estimate depth information. And but we look at this property, I mean by people working on multi-view stereo, in a totally different way. So basically, we are trying to come up with a function which takes a 3D coordinate and returns some scalar value. And if that 3D point is on the surface of an object, then that scalar value should be small. So basically, we have some 3D space and trying to evaluate this function value all over the space. Then wherever the function value is small, that is probably on the surface of an object. And I'll give you more intuition by providing some easy example. So this is one example of such photoconsistency function, which takes a 3D coordinate and returns some scalar value. Suppose you have so 3 cameras, 1, 2, 3 here. And because camera parameters are calibrated, you know where these 3 cameras are. And this is the one object, surface of an object. Of course, you don't know the surface. This is something you are now trying to reconstruct. So what we do is, suppose you are trying to evaluate the function value at this 3D coordinate. So what we do is we just take this 3D coordinate and project into each camera. We can do this because we know the camera parameters. And we look at pixel colors of these image projections. So we expect that these 3 pixel colors should be different because this pixel color is coming from this point on the surface, while this pixel color is coming from this point on the surface. So those values should be not consistent. Well, if you pick this 3D coordinate, then evaluate try to evaluate the function value in the same way. These pixel values are coming from the same place, so these pixel colors should be consistent. So for example, by computing the variance of pixel colors of these image projections, we expect that the function value should be small for the 3D coordinate, but high for this 3D coordinate. So what we can do is just sample points in 3D space and evaluate the function value. What we should expect is smaller values here, which are actually on the surface of an object, and higher value in the other places. So essentially, our problem is to evaluate this function in the 3D space and trying to find a 2D surface where this function value is small. I hope this makes sense. So now I'm going to talk about the main ideas of our approach framework. And there are actually more than 3 main ideas, but I just picked major 3 ideas. And first is a patch-based surface model. Typically, when you talk about 3D reconstruction, people are interested in getting a 3D mesh model or triangulated mesh model. But we use our set of smaller rectangle patches to represent the surface of an object. So in this movie, is actually pretty hard to see, but this is just our texture-mapped smaller planar patches densely covering the surface of an object. So we use our set of these rectangle patches to represent the surface of an object. And we use this representation for various reasons, which I'm going to refer later. And for each patch, basically, we just need to know the 3D coordinate of the center of the patch and also the orientation. So each patch, basically, we want to estimate these parameters for each patch, covering the surface of an object. And before getting to the second idea, I just defined the photo consistency function for a 3D point. But similarly, we can define photo consistency function for a 3D patch. So the idea is really simple. Suppose you have some 3D patch in the 3D space, and you want to compute some function. And if the function value is small, this patch is probably on the surface of an object. And what you do is simply just project this patch into multiple images. Then sample the colors of these 3D category 3 by 3 grid locations. So if this patch is actually correct, then these colors, the 9 colors, these 9 colors should be consistent or show some similar distribution. So we can just use any measurement, consistency measurement, like sum of scale differences or normalized cross correlation to compute how image textures are consistent with each other or not. So basically our problem is you want to find a 3D plane where this function value is good. And here's a second idea, patch expansion, which is basically making use of spatial consistency. So for example, you have some surface of an object, which is typically smooth. So if you can reconstruct a single patch here, then we expect that there should be another patch nearby. So you can kind of keep on expanding those patches instead of exhaustively searching for the whole 3D space. So we have this kind of smart expansion procedure to efficiently cover the surface of an object. And the last idea is how to handle occlusions such as pedestrians. And in this example, for example, if you want to reconstruct this structure, you want to use these 2 images while ignoring this one to do 3D reconstruction. But how do you do that? And it turns out that actually a really simple trick can do the job. And the trick is as follows. So suppose you have some 3D patch, which are kind of projected into these 3 regions. What you want to do is to use only these 2 images, ignore the third one, to do 3D reconstruction. And then what we do is simply we just compare textures. So if you compare this texture, by using the photo consistency function I just defined. So these 2 textures look similar. Well, these 2 textures look different. Also, these 2 textures look different. So we can basically tell that, oh, this must contain some obstacle outlier. So what we do is simple. Just compare textures. And by setting some threshold, we can detect that this is outlier. And use only the inline images to do 3D reconstruction. So it's a really simple trick, but it turns out it works really well. And I'm going to show you some results later. So I'm going to talk about the details of the algorithm by using these ideas. And the algorithm consists of 3 steps. And first, we detect features. And I use the kind of 2 popular feature detector in computer vision, which is the Harris corner detector, which is supposed to detect corner-like features. And the second feature detector is our difference of Gaussian, which is supposed to detect blob-like features. So here's one sample input image, and we run feature detector, and we get some result. And also another image of the same object from a different viewpoint, and run feature detector, and get some output. So in the second step, we try to match those features to generate a sparse set of initial patches, which are going to be expanded in the last step. So in the second step, we try to match features to generate patches. And the idea is, I guess, pretty straightforward. In this toy example, you have 3 images. And so this grid is basically, you can think of a parameter to control the resolution of the output. So we are trying to get at least a single patch in every cell. So if you really want a high density reconstruction, you just put beta to 1. So you want to get at least 1 single patch in every single pixel. Or you can set this beta to 4, which means you want to get a single patch in every 4 by 4 pixel squares. But anyway, our goal is to get at least a single patch in every single cell. And in the second step, what we do is we just pick 1 feature in 1 image, then trying to match this feature in another feature in the other 2 images. So if you know camera parameters, then we know that this feature must correspond to some feature along this line. There's a special line called epipolar line. And you don't have to match this feature against, like, for example, this feature. You know that the corresponding feature must be along this line. So we pick this feature and find a feature along this epipolar line in another image. Suppose you find one. So what you're trying to do is now trying to match these two features to generate a patch. Then if you assume that these two features match, you can actually estimate the center of the patch by simple triangulation. You have two images, camera parameters. If you assume that these two features match, then we're just shooting ray and compute intersection. We can roughly initialize the location of the center of the patch. So we initialize the center of the patch by simple triangulation. And we initialize the normal of the patch, the orientation of the patch, by simply taking the optical axis of one camera. So this is a really rough initialization. Now we are going to refine these parameters in our kind of simple optimization. So before optimization, we like to use as many images as possible to refine these parameters. So because we have not good initialization, we also, again, project this 3D coordinate into all the other images. So these three features could possibly correspond to the same 3D feature. And what we do is what I just explained before. Assuming that these three features match, we detect outliers by simply comparing image regions. And by using only image inliers to refine these parameters. And for the optimization, we have some function to optimize. I defined for the consistency function, which is defined by 3D patch. We basically want to find this parameter, like 3D location of a patch, orientation of a patch, so that this function value is going to be optimized. So this is a simple optimization problem. You have some number of parameters to parameterize the patch orientation location. You have some single function for the consistency function to be maximized. So you put into this function and variable to the optimizer, and you get the optimized value. And I just use the conjugate gradient method for the optimizer. So again, I have some initialization, C of P, N of P, 3D coordinate of the center of a patch, and the patch normal, and put into the optimizer to maximize for the consistency function. And I got the result. So if you, after optimization, if your for the consistency function is more than some threshold, or the patch is successfully generated, so I take this patch and kind of mark this cell as gray. The patch has been reconstructed already, so I'm not going to do any reconstruction for this cell anymore. So you keep on doing until all the cells has been marked or all the features has been tried matching. So we keep on doing the same thing. So after this, we have some initial set of sparse patches, but they only correspond to the features on the images, and we want a dense reconstruction. So we are going to apply some patch expansion and also filtering, because this naive feature matching generates some false positives. So we need to filter out some bad false positives while making the patch reconstruction dense by expansion. So the patch expansion is just, I explained the main idea. It's really simple. So this is something we expect. We have some surface, and the patch should line up nicely adjacent to each other. So suppose you have reconstructed one patch here. Then we expect that there should be another patch along the same plane. So we initialize, again, the patch location and orientation of a patch by simply placing neighboring patches on the same plane. Then again, optimize this location orientation by maximizing the photo consistency function. So like this. So suppose, again, both patches have succeeded in optimization. Next, we just take next patch, assuming that there must be our neighboring patch here. So we place it, initialize it, and put it into the optimization. Then you get some result. So you keep on doing kind of smart about expanding patches on the surface of an object instead of searching in whole 3D space. So the another thing we have to do in this step is to filter out bad patches or incorrect patches. And here's a typical situation where bad patches occurs. So we have 4 cameras. Then this is a red patch. It's an incorrect patch, and which kind of reconstructed here by mistake. And you have a set of like 4 patches which are correct patches. And for example, if you look at this patch P1, when you optimize patch P1, for example, you use this image I4 as an inlier to optimize the patch. So patch P1 thinks that I should be visible in this camera. And also for patch P2 thinks that I should be visible in camera I3. So there are some visibility inconsistencies happening. So what we do is for each patch, For example, for patch P0, we collect a set of patches which are inconsistent in visibility information. So in this example, for patch P0, all these 4 patches are inconsistent or breaks the visibility consistency. So there's some collision here. So I just compare the photoconsistency function value at P0 and all the photoconsistency function value at these 4 patches. And obviously, because there are so many patches here conflicting in visibility, so P0 should be an outlier. So you can kind of guess that this should be the incorrect patch. So we can reject these incorrect patches. And here's another situation where the incorrect patch, again, P0, is inside of the true surface. Again, same thing happens. So P0 kind of are inconsistent in visibility information for camera I1 against patch P1. So there are 2 patches that are conflicting in visibility information for this patch. So again, we can reject this P0 as an outlier. So typically, we iterate this filtering process and expansion process a couple of times. We can expand, filter out bad patches, and we expand 2 or 3 times to get a final 3D reconstruction. So I'm going to show you some results. Here is our sample image of our kind of object data sets, where there's an object and images taken kind of all around. And typically, there are many images from like 15 or 20 or 30 to cover really from all around. And for these examples are only 4 images, kind of only from the front. And here is our, stop it, it's not powerful enough to show play in both. So this is just showing the texture map reconstructed patches. So this is, you are now looking at a bunch of tiny rectangular patches with a texture mapped on. But because they are so dense, it doesn't look like our set of patches. But this is just the raw output of the algorithm. Again, for both data sets are just coming from 4 images. And before showing more results of course, you're just getting a bunch of patches, so which is doesn't have any connectivity information. And people are interested in mesh model. So we have to kind of convert our patch model to mesh model. And there are some existing work. For example, Kazudan, he has some algorithm and kind of free Windows software binary, which kind of converts a set of patches into 2D manifold automatically. And there's also some another method which was originally presented by Brian Collis and Mark Levoy, which is actually for the laser range scanner-based methods. But there's a couple of methods to kind of convert patch-based model into our surface-based model. And in this work, I picked this approach, kind of called iterative deformation, which is actually simple. So first, we somehow build a polygonal mesh model as a kind of initialization. So if you know some foreground background segmentation, you can build a visual hull model, which gives you kind of initial mesh. And if you don't have our segmentation information, then you can, for example, compute a convex hull of centers of reconstructed patches as an initial kind of surface. And there's another way of kind of initializing the surface. So this is the kind of visual hull for one data set. This is the convex hull of centers of all the reconstructed patches. And here's another way of initializing the mesh. And what we do is basically trying to snap the vertices on this mesh onto reconstructed patches. So you have initialized your mesh somehow. Then you have a detailed reconstructed patches, basically trying to snap those surfaces onto reconstructed patches one by one. So here's the results of all the object data sets. So you see for each data set, you see a sample image. Then these are reconstructed patches, and these are the final mesh model, and from 2 different viewpoints. Maybe a couple of things to note is for this example, you don't see much texture, basically kind of white, and basically using kind of shading information to the 3D reconstruction, and it works really well. And this is one example with our kind of complicated geometry. For example, this eye socket is a really deep concavity, and typically it's really hard to get this kind of high, deep concavity by image-based modeling algorithm. But because we use kind of flexible patch model, and if you notice that we don't have any good regularization in the algorithm, so we can easily handle those huge concavity or huge depth gap in the reconstruction. And so this is another example with a skin texture, which is really weak. You don't see much texture, but we can actually match those textures to get a nice reconstruction. And here's the movie of the reconstructed mesh model. So this is an example with our big concavity here of the eye socket. It's typically difficult to obtain. And on the right-hand side, you see this is a kind of massive data set about, I guess, 48 images and high-resolution images. And I guess the reconstruction is almost accurate, except a few places. For example, here, this is actually a garbage, our kind of whole structure. And this part cannot be reconstructed simply because this is a kind of cape and seeing the structure behind it. So there are not many cameras. Probably only a single camera looks at the surface. And to do 3D reconstruction, you have to at least 2 cameras to look at the structure. So this is a place where really we couldn't do anything. But for the other parts, I think we did a pretty good job of reconstructing the structure. Here's some other example. This is the movie I showed actually at the beginning. It's only 4 images, but I guess you can get lots of sharp details and like my facial features. Also some buttons. You can get really high detailed structure only from 4 images. Yeah. And here's again from 4 images on my whole body. And so originally I thought this was a really tough example because of the genes. So genes, black, which means absorbs lights. So it's kind of hard example for image-based modeling methods because you don't see much photons coming from the genes, but we can get lots of details. And here's our result, our sample image for our scene data sets. Scene means kind of we have some structure and picture taken from like one side. And this is our interesting data set in terms of water, because water looks different from different viewpoints. So in this example, we expect the algorithm to kind of ignore these water regions and just do 3D reconstruction here. And for this example, I kind of manually painted this red human to this data set to kind of add like obstacle outlier. So this is a real example with the obstacle outlier. And I have some movies to show, but first of all, just static images of the results. So for this example, as I mentioned earlier, there are pedestrians in front of it. So you want, for example, you want to get this structure. Then you want to use these second and third image while ignoring the first. And as a result, that you can make some texture-matched patch model. And when do you use texture mapping? You can use images which does not contain outliers. So when in this visualization, you don't see any pedestrians in this rendered image because we know which image region contains pedestrians. We can just use the right image texture to do texture mapping. So we can kind of magically remove people from the input images. And this is another example with the outliers. And so this 7 images, and this is the result. Again, we can kind of successfully identify this region as outlier, and ignore those regions and just do 3D reconstruction where those people don't appear. And for this result, one thing I did is to replace, I guess, the 5th image by the 3rd without changing camera parameters, which means the whole 5th image becomes a garbage because camera parameter is different. So you just replace this image by this. So the algorithm has to identify the whole 5th image as a garbage and ignore the outlier, and also ignore this red image region outlier, then do 3D reconstruction, and we can still do. And of course, we are missing some part of the structure because probably there are not enough cameras looking at this structure, so we cannot do anything. But instead of creating garbage, we just reconstruct structure and leaving empty space where there are not enough information, I think, which is a good thing. And another interesting example is so this data set. This is just a building structure. But one interesting thing about this data set is for some of the images, our pictures are taken really close. So you have about four pictures taken from far from this structure. Then you have a couple of images taking this structure really close. So if you remember our algorithm, the number of patches or the resolution of the reconstruction depends on the images. If you have the close-up images, we are trying to reconstruct more patches for those places. So the resolution of the output is kind of adaptive automatically. So if you have some images close-up, then for that image, we are trying to reconstruct higher number of the patches. So this is one advantage with the algorithm, that the output resolution is kind of adaptive. So you have close-up images, you get more patches. And this is shows our reconstructed patches for some of the other results. This is an example, if you remember, with some water behind it. So actually, you can see, the movie has some artifacts, but from this region. Oh, yeah, actually, yeah, stopped already. And this contains some fake patches here, which probably corresponds to water region. But this is the only mistakes, and we didn't create garbages for the rest of the LR image. And for this example, again, because we know this is an example with the pedestrians in front of it, and because we know which image region contains obstacle, which image does not. So we just use image region which does not contain obstacle to the texture mapping so that we can kind of remove pedestrians in rendering this movie. And also probably you can see this pole standing here. I guess it's difficult to get this structure if you use like a mesh model based methods, because we use flexible patch model, we can get this kind of structure quite easily. And here's just our final 3D mesh model, which you converted from a set of patches. Next. So I've shown you like pictures of movies, and of course people are interested in asking, so how are they accurate? And so fortunately, there's some quantitative evaluation of multi-view stereo algorithms, which was published last year at CVPR. So basically, provide some data sets. Then people run their own algorithm. Then submit results. And they're going to evaluate your accuracy of the results compared with the ground truth and show you how much accurate your results are. And for example, if you can, let's see, maybe I'm not connected. I can go to the website. Yeah, so if you type multi-view stereo, I guess the first link is going to be the evaluation, which is done by Steve Seitz and Rick Zielski. So currently they are providing datasets for 2 objects, but total 6 datasets. For each object, they provide 3 datasets. They are different in the number of input images. Then people just run your algorithm and submit results, and you're going to see results by clicking the main table here. So they're a whole different algorithm you can see, and the algorithm I just explained are going to be listed like here, and you see like 2 numbers. So this table is so you have one temple data set. 3 different data sets. They're just different in the number of images. So you see the sparse data set, which consists of only 16 images. They have some intermediate data set, 47 images, and a really dense one, 312 images. And you have another data set, the white dinosaur without much texture. Again, 3 different data sets with a different number of images. And for the green number, for the blue number, basically says the accuracy. So they use laser range scanner to capture the kind of ground truth 3D model, basically computing distance from the ground truth model to your reconstruction. So it kind of says that on the average, your reconstruction within 0.65 millimeter from the ground truth. So the smaller the better for this blue number. And the green number is kind of completeness. So this number is higher the better. Basically that how many percentage of the reconstruction is within how many are a certain number of distance from the ground truth model. So basically that if the blue number is small, which is good. If the green number is high, then which is good. And so our algorithm, this Furukawa 2. Actually, there's a Furukawa at the top. And our result is actually the best in terms of both these blue numbers, green numbers, and in these 4 categories. So all the dinosaur data sets and 1 sparse temple data set, if you compare, for example, so our result is like 0.42 millimeter accuracy, which is better than all the others. And again, 99.2 coverage, and which is better than all the others. And one thing I found interesting is so our result for this sparse data set, only 16 images, actually better than any other algorithm on their dense data sets. So these people use more than 300 images to 3D reconstruction. But our result on only 16 images is actually better. So I guess you can tell that our algorithm is really good at handling and processing the accurate 3D model. Let's see. Oh, so starting. Yeah. So here's some of the pictures of the reconstruction model by 4 different kind of top performing algorithms. So this is our method, and these are the other 3 kind of top performing algorithms. And you can see that even qualitatively, you can see, I guess, difference. So we can reconstruct this kind of sharp structure here or there, while many other methods going to fail in getting structures. And even qualitatively, I guess, our result looks probably better than the others. And but of course, getting good numbers in this kind of evaluations is a great thing because people pay attention. But I guess it's really kind of confusing because people just look at numbers and think that, oh, this algorithm is good, this algorithm is bad. But we like to emphasize that there are whole different kinds of properties of the algorithm, which is superior to the other algorithms. And in addition to the accuracy I just mentioned, I guess we can list a couple of things which our algorithm is better than the others. For example, our algorithm just takes images and the camera parameters. And the multi-view theory is supposed to work with just images and camera parameters. But typically, there are some hidden inputs in addition to these camera parameters and images. And those such hidden inputs are, for example, visual hull or bounding box or valid depth ranges. And in our algorithm, we do not use any such information. But many other algorithms kind of need this information to kind of start their process. But we do not need any such additional input, so which is one advantage. And of course, we can handle a variety of data sets. So I showed you results of object-like data sets or scene-like data sets. While many of the algorithm in the evaluation is kind of focused on only object-like data sets. So our algorithm is really a general framework and can handle a variety of data sets, but still is, I guess, shows kind of better results or best results in kind of object-like data sets. So I guess this is one advantage. It's a really general algorithm. We can handle different kinds of objects. And the other advantage is using a patch-based model because there's no regularization or smoothness. So we can handle, I guess, complicated structure like a deep concavity. Another thing is occlusion handling. This is just one kind of simple trick, but we can handle pedestrians in front of the building and etc. This is the difference from the others. And the last thing is this is also one thing I mentioned that if you take pictures of an object from different viewpoints, and if some images are really close up, then our resolution is going to be higher for those images. So you can just take pictures at random, and the algorithm knows that for this structure you have the close-up, so the resolution of that is going to be higher, etc. So I'd like to mention about the future work, what we can do after this. And so one thing is obviously to extend this model to incorporate some temporal component. So if you want to capture some motion, so far we've been just looking at static frame reconstruction. But suppose you have some motion like facial motions or some non-rigid movement, then we like to capture structure at each frame, but also estimate some motion, which can be done by adding some temporal component to a patch-based model, and which already have some results to show. Let's see. Although I don't have time to explain details, but what we are trying to do is, for example, you see some 8 synchronized video cameras, 8 multiple synchronized and calibrated video streams. And what you want to do is to basically reconstruct structure frame by frame, but also estimate motion frame by frame. And this actual data set which is now presented as SIGGRAPH, this is for our close motion capture. And let me just go back and play. So for this data set, but they use the fact that they know how those triangles laid out on the pants. So for example, if you look at this triangle, like red triangle, blue triangle, yellow triangle, for their method, they know that if you know the patterns, they know that where this triangle should be. For example, like a left leg has some special patterns. So they remember how those colorful triangles laid out on the patch. But in this framework, we just want to show that you don't have to remember those textual layouts. You just use multi-view stereo constraints to do motion capture and reconstruction. And you see the results here. Oops, here. So here, again, we basically reconstruct a set of patches for one frame, the initial frame. Basically keep on tracking patches frame by frame. So this is the direct output of the patches. This is just with a texture mapped on. And we can estimate the velocity field, actually translational velocity and rotational velocity field. And so these actually blue arrows show translational velocity field. Actually, it's really hard to see because it's so dense. The green one is the rotational velocity. And we can kind of animate the mesh according to this velocity field. So you see kind of dynamic mesh model on the right-hand side.
How do you match patches over time?
Sorry?
How do you match
Suppose you initialize the patch in the first frame. So you know how the texture should look like in the first frame. So basically, you're trying to find the optimal 3D rigid transformation frame by frame. So it's kind of purely tracking, same as kind of good old 2D tracking, but we do tracking in 3D. So another thing which I think we can do is to kind of remove obstacle from movies, kind of movie editing. So this is one kind of proof of concept movie which I showed you earlier. So in this example, you have only 3 images as an input. Then you see like pedestrians in front of a building. So we can make this movie without showing any pedestrians. So I guess, if you take the movie which contain like people in front of the building, what we can do is to identify image region which contain obstacle, and kind of magically remove those people from the movie. So kind of lots of things should be able to be done by using the fact that we can detect like image region containing obstacle, an outlier. So this could be another interesting application. Oops, I stop it before showing the acknowledgement section. Let's see. Actually, this is the end of my talk, but just want to show the names are people who contribute to this work. And thank you, everybody, for your attention. So I'm happy to answer any questions. Yeah.
So how well can you deal with cameras with limited depth of field?
Oh, limited depth of field. So that's actually a good point. So for all the data set, pretty much I really carefully set up the camera. So everything is in sharp. And actually, there's one data set I don't have any result, but I have an example where some of the image surface is kind of out of focus. But actually, our algorithm worked. And actually, it's kind of hard to, of course, the surface reconstruction becomes noisy. But we can still, the algorithm didn't fall apart. And I would say, so if you have limited depth of field, we can get structure, but the quality of the reconstruction degrades at those places. But if things become too kind of blurred, out of focus, I guess our algorithm falls apart and you do not get any reconstruction.
So the function that you use to filter patches is simply the difference between the photo consistency of one patch and the sum of the photo consistency of all the patches that conflict with it.
Yeah. Yes.
Are you assuming that you know the camera poses perfectly? Because if you have 3 cameras, they are all off by 0.
You mean like errors in camera parameters?
Yeah.
Also, that's also a good question. So I would say that our algorithm is actually good at handling bad cameras. So I've showed you one example where I kind of manually change the one image by the other without changing camera parameter, which means camera parameter for this camera is totally screwed up. But because our algorithm has like a system to detect like image which is bad. So I always, whenever I compute this photo consistency function, I identify image which looks bad. So ignore those images.
Right, but that would be a case where you have multiple perfectly aligned cameras, one is really off.
Yeah.
But I'm saying that in the case that you have 5 cameras, they're all slightly inaccurate.
Oh, all slightly inaccurate.
Usually you always find only 2 pairs that match, but there's no third one that really matches.
Yeah, so I guess in that situation, for a structure, if you see, for example, 2 cameras which are somehow consistent, we use that 2 cameras to reconstruct. And for this surface, we have another set of cameras which are consistent. We use that camera to reconstruct. But because these 2 cameras have some errors, so you see some bumps or noisiness in the reconstruction. So I assume that, because I haven't experimented with such data set, but I assume that you get some structure which is just noisy, but doesn't fall apart. Let's see, for some of the sequences I use the calibration grid. For some of the sequences I didn't use any calibration grid, just use structure from motion, kind of detect features in the image and match them, and kind of computer vision algorithm to automatically give you camera parameters. Yes?
Can we somehow automatically determine the position of the cameras if we have enough images?
Sorry, what's the last one? Optimize, estimate camera parameters.
Assume that we do not know where the cameras are. Can we determine it somehow from the images if we have plenty of them? Can we just match features somehow? Because I feel that there are many applications when we just have an image or a movie and we do not know the exact positions of the camera.
Yeah. So I would say, so there's like a field of in computer vision structure for motion. So for our side, I believe that the camera parameters are given, and this is not our problem. So except that those people working on structure for motion, so they have a smart way of matching features from like different viewpoints, and do some robust like matching algorithm to estimate camera parameters. So, but I guess one thing I can say is, so if once you have a set of camera parameters which are good enough, then we can run this algorithm to get some matches. Then by using those matches, I can refine camera parameters. Because matching features is as difficult as getting camera parameters. So I guess we can help each other, estimating camera parameters and doing dense reconstruction to help each other kind of iterate between those steps to refine camera parameters further. Yeah.
So it seems the algorithm can be initially parallelized on a patch basis. Have you had an experience with that? Have you actually run it in parallel on several machines?
Oh, you mean speeding up all those?
Yeah.
Well, actually, no. Because I don't really care much about engineering efforts. So this is actually kind of slow. When optimizing those patches, I guess I did just use a numerical derivative instead of analytical. So far, I didn't care much about speeding a lot. But I guess there's opportunity of speeding things up. Because one work by Jean-Philippe Pons, he used a GPU to do a multi-view stereo. It runs really fast. And I guess we can kind of, as you just mentioned, optimize patch in parallel by using GPU to texture mapping really fast. But I didn't care about those engineering efforts. Yes?
Point samples to patches?
Sorry, algorithm from point samples to patches?
Yes. Did it move from one to the other? Did you start with positional information about the patches only, and then move to include the normal vector as well?
Sorry, what's the question again?
The way I did things ages ago was primarily based on just extracting feature points, mapping them to 3D, and treating them as points rather than as centers of patches.
I see.
Did you go that route at all?
Oh, I see. So I guess one answer is I'd like to use some patches and points. First of all, because of expansions. If you know patch orientation, you know that there should be a patch, adjacent patch nearby here, because we know the normal direction. But if you have a 3D point alone, you don't know where the adjacent point should be. You have to kind of search in whole 3D space. And the other reason is, so if you have a 3D point, so basically you're comparing pixel by pixel, or you have a patch, some region, you're comparing image region by image region. And I guess it is kind of true that if you image region by image region compare to things become more robust. So I guess that's the two main reasons why I want to use patches instead of points. Yes?
What methods do you take to areas with low texture like a blank wall or repeated texture like brick walls?
Oh, I see. So for the second part, for the repeated textures, there are, so one, let's see. I may not have a good example, but one, I guess, answer is, so if you have, for example, 3 cameras, they have some repeated texture, maybe like this. And actually, it is really difficult to match this line with this line if you have 3 cameras. So maybe not into, so you have only 2 cameras, and you take picture from 2 viewpoints. Then there is a like 3D coordinate where this pattern matches actually this pattern. But you have 3 cameras, it's actually really less likely to happen. There's such a coincidence. And you have more cameras that, even though your textures are kind of repeated, I think it's less likely that are kind of different similar patterns from different positions actually matching in 3D space. First one, sorry, what was the first point? No texture, I see. So actually, lots of questions asking me that question, and I guess that's a good point. So I guess the data set which does not contain good texture, I guess, here, is this object. And if you look at this region, it looks really homogeneous. And I guess I can just go to the website. And I guess it turns out, although for our eyes, you don't see much texture on those homogeneous region. But I guess actually there are textures. Let's see, here. So this is this white dinosaur data set. And here is my reconstruction to view 1. Yeah. So actually we are doing a pretty good job, which means there's a slight gradation in shading. And we can actually capture the patterns and match across multiple images. But there's a situation where actually there are no texture at all. It's really just white, and you can really distinguish between the other regions, and which actually occurred in one part of this data set, which from the different viewpoint. I guess it's hard to see, but for this region, you see some bumps, which is a fake structure. And I guess for this data set, this region doesn't have contain any useful information. And all the other methods fail in getting this structure. For example, some of the good ones, let's see. So this is a good algorithm. So again, basically messed up here. So I guess this is a situation where there's really no good information to extract based on multi-view constraint, and things fail. Kind of regularization. For our work, I haven't really done anything. But what happened is we didn't get any patches here. So there's no information so in getting a mesh model, we somehow can interpolate, add some regularization to get a nice surface. But many other methods have some regularization. So the information is noisy, then you get some smooth surface. Yeah.
So it looks like in the test set you have like mostly diffuse surfaces. I was curious what would happen if you have like more specular.
I see. So I guess see. So if your object like metal, super specular, doesn't work. And for some objects which have some specular, I guess we may not have a good image to show. So here. So there's one object which is not really specular, but you see some specular highlights for one image. But specular highlights we consider as obstacle outlier, same as pedestrian. So in our framework, if you have some surface of an object which is visible from multiple viewpoints, and if you see specular highlights in one image, we just treat it as an outlier image. You ignore it and use all the other images to do reconstruction. So if your object is not too specular, you can handle.
What about like semi-transparent objects?
Oh, semi-transparent, that's even tougher. Well, I guess it doesn't work at all. And of course, if your object is semi-transparent, there should be another computer vision algorithm to do 3D reconstruction. So this is assuming that should be some matte-like property on the surface material. Yeah.
My question would have been along the same
Oh, I
lines.
see.
If you ever tried in areas where you have windows, where you
Oh, I
have
see.
reflection
Mhm.
basically
Yeah.
every point.
I guess I haven't tried like glasses or windows. I guess if you use like windows to 3D reconstruction, you see some reflection. For example, you have some window reflection of that structure. So I should be able to get that structure, which is mirror reflected on the other side. It should happen if you see clear texture. So I guess, yeah, no other questions. Yeah, thank you very much for coming.